Ready to go? Okay. So we have made this transition. We've been talking about conservation of first mass, then momentum, which allowed us basically to do the Bernoulli equations to look at flow in viscid fluids. And now we've modified that to be able to look at conservation of energy, which allows us basically, if you recall, to recover a Bernoulli-like equation, but one which is written in one of two ways. We can write it either in terms of enthalpy, where this is basically defined as internal energy plus pressure over density in this particular case, and is defined again between upstream and downstream in some kind of stream tube that we know. And just for our own edification here, it has to be written between upstream and downstream. So the velocity is always a streamline velocity, as you'll remember. Mass rates, when we talk about them, are always positive because they can't be different. They don't really have any, doesn't change as to in or out, they're just positive. So I guess that's one thing to remember. This is always a positive magnitude, has to be a positive max rate. Velocities are always positive streamline velocities. In here we have the option to have maybe a certain amount of work done through pumping and a certain amount of head lost through viscosity, which is our loss. And so these equations are equivalent to each other, these two. They're just written in a slightly different way. Always written between upstream on the left-hand side, downstream on the right-hand side. Pumps magnitudes are positive if they're pumps. They're negative if they're a turbine, if you're getting energy out of the system. Head losses are always positive. Z is always in the positive upwards direction in our sign convection. And this value alpha is between 1 and 0. If it's 1, it means the flow distribution, the flow velocities across that stream tube is uniform, and if not, it's less than 1. And so that's basically where we were last time. So it allows us to be able to do calculations to look at whether there's heat supplied into the system, which is positive if you're supplying heat into the control volume, or if you're supplying work into the control volume, like a pump, for instance. And so you just need to take account of those sign conventions. And finally, if we want to be able to evaluate the two magnitudes of these pump gain in the system, it's the amount of power, the shaft work. Rate of shaft work is Newton meters per second, so it's power. Watts, in other words, worth of watts. Mass flow rate and gravity. And the head loss is always positive because the velocity is always going to be positive, v squared. This is a streamline velocity and some coefficient. Coefficient has 0 dimensions. If you look at the dimensions of v squared over 2g, v squared over 2g, it's units of length. And so this has to be non-dimensional. And it's a property. So typically if you look at piping systems, which we will look at, then a 90-degree bend or a 60-degree bend has a value of this loss factor, K sub L, which you can just plug into your calculation as you write Bernoulli from your upstream of your hose through your pipe system to your downstream location. So that's our utility of this. What else? That's probably about it. And so we have both of these magnitudes which we can pump in. We'll find out more about this later when we deal with pipe internal flows, and we'll deal with it. So what I was going to do today was I was going to go through a couple more examples just to use this set of expressions. Primarily the second one, which is Bernoulli, of course, with head loss in it. And then we'll talk about trying to use the next step. We won't do it, but we'll talk certainly in your other classes. If you're environmental systems engineers or petroleum engineers, you'll certainly look at porous media flows in the subsurface. And all of that follows directly, really, from what we've been talking about in terms of our conservation equations as well. So depending on where we get, we'll move to look at that. Okay? So if everyone's okay with that, maybe we'll just go through a couple of examples just to cement this in our minds. 2, I think, actually. So here's a question. It's out of the one of the ones in the back of the each chapter, chapter 5, I guess, just from the number. Pump transfers water from a large reservoir to another one, so it's going uphill from this point to this point. Difference elevation is 100 feet, so we know that. Friction head loss in the piping is given by this. If you can see it, it's K loss V squared over 2G. I guess the important thing to remember is that the velocity term that you're dealing with is in the pipe. Always. Or in the fitting. In the pipe or in the fitting. Not in the reservoir. So that's one thing clearly, because it's scaling with what's happening in the pipe. Where V is the average fluid velocity in the pipe. Okay, I guess it says that. And some loss coefficient. The relationship between the total head rise across the pump and the flow rate through the pump is given in the figure. This is this here. And the magnitude of this coefficient for pump pipe loss is that K sub L is equal to 20. Has no dimensions, as we said before. So the question is, what's the flow rate through the pump? So this is the pump characteristic curve, I guess. It says that if you're only flowing a very little bit of fluid, then it can actually pump against a big head, and it can provide a lot of power because it's not working flat out. If it's moving a big volume of fluid, then it really can't push it very high, which is kind of what you would think. Actually, if you think about it, this looks just like our force versus velocity curve that we use to talk about the amount of work in a system, right? If the force is equal to, if the velocity is equal to 0, but the force is big, there's no net work done. If the velocity is big, but there's no force in the system, there's no work done. And it's only in the intermediate part of that strip. So I guess it's not quite that plot, but it's somewhat reminiscent of it in terms of this is kind of measurement of a force. And so if you wanted to, you could fit an equation to this, and this is the equation, just by observation. It's a bit like the meniscus in the vinometer type question. You're trying to fit an expression to it. And you can check, for instance, that this satisfies the endpoints, that, for instance, when the flow rate is equal to 2, then Q is equal to 2, and the pump head is equal to 0, which is exactly what it should be. When the flow rate is equal to 0, this point here, then this is equal to 2 times 100, which is 200, and it's right here. And it's just a linear distribution between that. I guess should be careful with this, of course, because the one thing that this violates is that it violates our dimensionality criterion, right? This is units of length, and this is units of length cubed per time. And so there's some hidden dimensions in here. So this 100 is not really 100. It's some hidden dimensions. I guess the dimensions would be what? It would be seconds per feet squared, right? So in other words, feet cubed per second has to be multiplied by feet squared seconds to give you length, right? So this 100 is in actually units of seconds per feet squared. Perhaps it's not a big deal, but just stick that away in the back of your mind. Of course, if you work in petroleum engineering, every single equation they ever use has dimensions embedded into it, is not dimensionally homogeneous, and you have to use centipoise, and you have to use PSI, and you have to use inches per gram, and all kinds of bizarre units. Anyway, so just bear that in mind. So we digress. Solving the problem. This is my favorite way of writing Bernoulli's equation, always in terms of lengths, just because lengths are kind of manageable. And you know that if the lengths that you get in your problem are in thousands of kilometers, then you know you probably don't have the right answer. So these have to be in tens or hundreds of meters to make sense. So pressures. Pressure 1, atmospheric. Velocity 1, the big tank assumption. Oh, first of all, I should say, we're writing Bernoulli's equation between these 2 points. And we're writing them between these 2 points because we suspect that we can probably throw away a lot of the terms. Elevation is equal to whatever we want to choose it, probably 0. Up at the top, pressure at point 2, again atmospheric. Velocity at point 2, again, the big tank assumption. And elevation, if this is our datum, equal to 0 here, then this is going to be 100 feet. You can't see that, right? I'm always curious as to whether I'm writing off the top of the screen, but I'm not. So, pow, 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 100, I guess. We know that this is equal to this head loss, V squared over 2G. We have to remember that it's not either V1 or V2, but V pipe. I'm not sure what to call it. So we have to figure out exactly what that is. And we also have an equation for the pump, which is written in terms of this, head loss rather, which is equal to 2 minus Q multiplied by 100. And so we have one equation. The terms we have left are going to be this term, and this term, and this term, only 3 of them. And so we really only have one expression, but presumably we have 2 unknowns. We have a velocity here. And so we can write the velocity at point P. Do we know the velocity in terms of the cross-sectional area of the pipe? Do you know the pipe diameter? Don't see? Oh, yes, yes, yes. So what is it going to be? Velocity at point P is going to be equal to the volumetric flow rate divided by the area of the pipe. Area of the pipe is going to be pi d squared upon 4. And so the bottom line is that now we have an equation written in terms of Q. This is a function of Q if we just rewrite it. This is also a function of Q if we rewrite it. And we know this is 100 feet. And we should be able to solve for the value of the flow rate through the pipe. And so that's basically this. So that's it. So you just need to go through it analytically, figure out what you do know, figure out what you don't know. Of course, you could write the point 1 at any point you wanted to. You could write it here for that matter, in which case you'd have a pressure term added to it, right? P over gamma, P1 over gamma. But it's just easier to write it on these points. You'd get exactly the same expression with this because you'd know, if you choose the depth of this tank, then you'd know what P gamma is and you'd know what this different elevation would be, and you'd just be adding it to the elevation difference. So that's it. So this is Z2, right, at this point. So that's it. So it allows you to be able to solve it. I haven't gone through it, but basically you end up with a nasty expression which has a square in it. You have to solve the roots for it. Not particularly straightforward, but the bottom line is that you end up with one equation. You end up with having to substitute, so you only have one variable, and the logical variable in this case is just going to be the volumetric flow rate through the tank, and you can solve for it. Okay. So, and actually has a grain of truth to it in terms of pump losses in the system. Yes. No, none of that. So, yeah. If we're solving for heat in some way, we'd use the other Bernoulli equation, right? So, it's not...
Okay, so the other Bernoulli equation, that one,
it's not this. This is something else. Yeah, this is heat in. And so, in our equation here, this is Q is equal to velocity... Oh, did I do it right? It was velocity times area, right? Did I do it right? Did I write? Yeah, okay, I guess I did do it right. Yeah, yes, yeah. So in this case, it's purely volumetric flow rate. Okay. So second question. Gasoline flows through a pump. You have a flow rate going through the pump. Again, this would be Q in our terms as we've used it. Head loss between 1 and 2 is equal to this. This is our head loss equation. It's velocity, and if you probably can't see that. Oh, I only found out how to do this. Yes, I see it works. Oh, in full screen mode. Oh, look at this. Isn't that amazing? Instead of pressing my plus key, I can just do it with my fingers. So it's the velocity at, oh, isn't that lovely? I'm writing with the wrong end of the pencil, I'm so excited. So it's the velocity in pipe 1 in this particular case, not at point 1, but velocity at the location pipe 1. So it has to be at a location. And so we have a head loss, which is just this HL term. So in other words, I guess to write it out, head loss is equal to 0.3, which is our head loss term, times the velocity in pipe 1 squared over 2g. What will the difference in pressures be between sections 1 and 2? So the question is, you don't know what the pressures are here at pressures 1. And we don't know what the pressure is at point 2. But we do know some other things. Do we know velocities? V1. We certainly know the flow rate, if you like, Q2. So V2 is just going to be the volumetric flow rate divided by the cross-sectional area at point 2. I guess if you're not given a value for V1, then you can use continuity, because you know that the velocity at 1 times the area 1 has to equal the velocity at 2 times the area 2. And so in other words, velocity at 1 is just going to be equal to the velocity at 2, which we know, because presumably we know this, and presumably we know the diameter of the pipes, so we can calculate the area. So it's just going to be the ratio of the two areas. Right? And so we have this defined. Do we have the elevation? I guess we do. Z1 is equal to 0. Z2 is equal to 3 meters. And, well, they write the equation this way. I hate writing it this way, but that's fine. So I guess go with it this way. This is just exactly the same Bernoulli expression, but it's been divided through by unit weight, right? So, or multiplied through. If you multiply all these terms through by unit weight, you get this term, etc. And so it's just another form of that same expression, so it's no different. And we have to figure out what we know. So we know the velocity at point 1, because we related that to Q, which we know. We know the velocity at point 2, because we've related that to Q. We know the pressures. We don't know the pressures. So these are the two things that we want to rearrange the equation for, I suppose. We know the elevations. This is 0, and this is equal to 3 meters. We know the head loss is equal to this term here. And we just have to be careful to make sure that we use V1 to do that. And so this is also defined as a function of our Q. And what else do we know? We know the amount of work done for our pipe pump. So in other words, in our terminology, uppercase W dot is equal to 20 times 10 to the 3 watts. Newton meter per second. Right? And so that's big W. Big W. And in this particular case, so in other words, it's this. So in other words, HP is equal to this. I only draw a line through it because it's a scalar value. We've used it before for velocity, right? Relative velocity. This is mass flow rate and G. So that's the other expression that we need to be able to, which is also the same as, I guess in this one they use lowercase w. So this is the amount of energy, power, per unit mass flow rate. So all the lowercase w would be this expression here. So little w is equal to big W, power, pump power divided by mass flow rate. So I just have to keep that, just slightly different terminology. And so in this expression then, the only two things, if you rearrange things around, the only two things that we don't have is we don't have values of this pressure, the pressure drop across the system. And actually you'll see it doesn't matter what the absolute magnitudes of this is, it's just the change in pressure between these two places. And so we don't have a reference pressure to be able to calculate it from. And so we can rearrange this expression in terms of the two pressures on the left-hand side. We know what the velocities at 1 and 2 are from the flow rate. We know what the elevations are. This is 0, right? We know what this is. It's equal to uppercase W dot divided by mass flow rate, which is going to be equal to 20 kilowatts divided by the volumetric flow rate multiplied by the density of gasoline. So, just by terminology, from what we looked at before. And of course, this loss term is equal to, is also a function of velocity 1 squared. And so the only things we don't have are the magnitudes of this pressure drop, and that's exactly what we solve for. And so, yeah, so that's it. And so it turns out to be that the pressure drop is 197 kilopascals. Not very much, right? So atmospheric pressure is 101. So this is double the distance from us to absolute zero pressure. So you can work through that. But that's it. Yeah, go ahead.
If you show off the prompt, it says that the head loss is equal to that, but it doesn't have the gravity term. Should that have the gravity term?
Say it again, sorry.
There's no gravity term in the head loss in the prompt. Should there be a gravity term?
No, the gravity is taken care of by these terms here. This is basically the unit weight terms in the Bernoulli equation.
So then why did you bring the gravity term into your head loss equation?
Oh, you mean this equation, these two equations?
No, you have head loss equals 0.3, velocity 1 squared over 2g.
Oh, yeah. Oh, yeah, this is the head loss written in terms of length. So say your question again.
So should that gravity constant be there?
It is in this way of writing it because this this Bernoulli term v squared over 2g has units of length just because it's, you can tell here. So for this to be in units of length, it has to be written in this way. Oh, okay, in this expression. Yeah, okay.
Yeah, I'm just wondering how you do from that.
Yeah, okay. So they're defining their loss term not as a length, but as, yeah, okay, good point. So they're defining their loss term not as a length, but as a length divided by unit weight. So their loss term, by definition, is equal to our HP divided by unit weight, because all of these are multiplied by unit weight, right? So the units of this are pressure, the units of this are pressure divided by unit weight. So if we multiply this term by unit weight, we get this term. So unit weight is rho g. And so if this is equal to, their term is 0.3 v squared over nothing, right? That's interesting. 0.3 doesn't, that suggests then that it has to have a rho term in it. Oh no, it does have rho. So their term is density times loss is equal to this. Yeah, okay. Yeah, right. That bounces, right? Yeah. Thank you. Yes? Just scratching? Well, waving or whatever. So. All right? Okay. So yeah, so I mean I prefer, I think it's good to use a set of equations. When I remember Bernoulli, I always remember it in this form. So but you can always move between them. So always remember, certainly by far the more important equation for us to use is going to be the second one of these. As you can tell from what we've done, we used this once for a quick enthalpy question, and we've used this many times. And so I think it's useful because it's written all in terms of lengths. This has to be a length, and so you know that if the numbers are huge numbers, then you're probably you've probably dropped a dimension somewhere or not done a conversion correctly. Okay? All right, so what we're going to talk about. So I think those are the examples that we're going to do. So now we're going to talk about, oh no, one more. Let's do it quickly. I think just one more. Two more. No, you're just going to do one more. Yeah, let's do one more. So a very practical, pragmatic one of a dam. And the question is, how much power can you get out of a dam? And so again, Bernoulli equation, choose where to write it. Between point 1 upstream, point 2 downstream where this stuff comes out, where we know that the velocity is 6 meters per second. And we know the diameter, I guess, of the outlet. So we write Bernoulli equation, upstream pressure, atmospheric, 0. Big reservoir assumption, elevation, well, take this as 0. So this is 50 meters, bless you. This is what we don't know, I think. Pressure 2, going into the atmosphere. Effluent exiting into the atmosphere, just like a jet. We know the velocity, that V2 is equal to 6 meters a second. We know the elevation, we've said is 0. And we have some losses, which we don't know, I think, in this particular case. So again, they've written their equation in this way. So I don't know why they've done it in this particular way. You could just divide all these terms by gravity, and you'd have our Bernoulli expression in terms of length, but they're written a bit differently. And so what terms do we have left? We have this term, which is for the power, which is going to be this term here, just written in a different way. We're going to lose this term, we're going to lose this term, we're going to lose this term and this term, and this is going to be 50 meters, right? And so the only terms we end up keeping are, well, the difference between those two elevations. I guess we've kept this one, it's just 0 is one of them, right? The velocity, exit, some loss magnitude, and the shaft work. And so we know these absolutely. This is 6 meters a second. This is 50 meters head difference in gravity. And so we can calculate the magnitude of the this shaft work per unit mass flow rate. If you multiply shaft work per unit mass flow rate by mass flow rate, so this is just going to be what? This is going to be volumetric flow rate times density, which is the same as the velocity at 2 times the area at 2 times the density. And if you do that, you end up with the power out of it. Just have to keep your units straight and realize that a watt is a Newton meter per second, and you end up with a couple of megawatts coming up, okay, if there's no losses. You'd have losses as it flows down these the pipes, but they'd be relatively small losses because they're quite large diameter pipes, so the loss per unit mass flow would be quite small. Obviously, if you had tons of little pipes doing it, you'd lose lots of energy in the pipes, and that's not a good thing. And so I guess this would be the ideal case where the loss is 0, and this would be the absolute maximum you could get if your turbine was 100% efficient and you have no losses in the system. So this is the ultimate upper limit magnitude that you get from the system. Okay. All right. Went longer than I thought, but that's okay. So the other things, well, first I should ask. So everyone okay with that? So two expressions. The energy equation is really just Bernoulli equation written slightly differently that allows you to have viscous flows, flows that aren't inviscid, that have some loss attached to them, and also allows you to put some extra energy into the system in terms of a pump head or recover energy from the system in terms of a turbine. And I guess I didn't say it here, but if this is the case, if you did this in terms of the sign convention, the magnitude of the watts that you get out of this would be a negative number because you're not putting energy into the system as you are in a pump, you're getting energy out of the system in terms of a turbine. So the magnitude of this term here, as you calculate it, would be negative, which just means that you're getting energy out of the system by our sign convention. So that's worth remembering. Okay? All right, so let's, I didn't use my little scroll yet, I guess I can do that in another day. Why do today what you can put off till tomorrow, right? So, yeah, it's human nature. Come on. So this is an interesting. So what we've done so far is we've talked about conservation equations in a very simplistic way of volume in equals or mass in equals mass out in terms of streamline magnitudes. We did it in a more sophisticated way using Reynolds transport theorem for kind of arbitrary shaped volumes. But we can also do it to be able to solve problems in digital ways, digital computers. And for that, our way of doing things will slightly change. So just to perhaps make this point, I guess. Oh, what day is it today? Thank you. Hump day. The ultimate hump day. What does the ultimate hump day mean? Oh, exact middle of the... Yes, it is exact hump day. Yes, right. Not just... That's right. I know you can interpret that differently. I wasn't born yesterday. So it's fine. So it is hump day. So what I was kind of referring to... I love the fact that I just found out how to do this. It's really cool, isn't it? Woo. So the two ways that we've looked at things so far is that we've looked at things along streamlines to be able to define our control volumes like this. So this is kind of our Bernoulli streamline way. And so we know that we have a velocity in, we have a velocity out. Those are streamline velocities, which by definition are perpendicular to the cross section that we draw. Because each of these streamlines on the boundaries are trajectories of particles or molecules of fluid, then by definition the velocity across these boundaries is zero. So there's no flow across that. We've also used Osborne-Reynolds' transport theorem. So what was this? This was velocity 1, A1, rho 1 is equal to V2, A2, rho 2. Nothing more than that. We used Reynolds transport theorem. And actually Reynolds transport theorem, although we didn't do it this way, it could be for any kind of, the arbitrary kidney shape, that you have things flowing in, things flowing out, unit normals. And we convinced ourselves that Reynolds transport theorem said something like the volume of the control domain times the rate of change of density plus the density multiplied by the rate of change of this volume plus the mass flow rate is equal to 0. And of course this mass flow rate is not, of course, was equal to a velocity normal to the boundary times an area times a density, bit of an integral in there if you want to get really fancy about it. And so that's kind of our statement. And so this is really convenient for us because we could make this go around any shapes we wanted to. I think I recorded it, but we didn't do it in class. We did the Jetlev guy, we did a vein that was moving. We're able to do that. But another way to do it, so this, if you like, is an integral approach. And so, of course, you can imagine if there's an integral approach, you can imagine that counter to that, there's a differential approach. And you can get the differential approach merely by changing the shape of the system that you're dealing with. And if you do that, then you won't be too surprised that the shape of the volume you deal with would be something like this. Right-hand coordinate system, x, y, z. The lengths of this would be a length in the x direction, a length in the y direction, a very small length in the y direction, and a very small length in the z direction. And we'd have things like velocities in the x direction, etc. And so the interesting thing is that what you could do is you could apply to this same approach, Reynolds transport theorem, product of volume times the rate of change of density, the density times the rate of change of volume, and the mass in minus the mass out, and this should still hold. But now instead of using this kind of arbitrary shape, then the areas of these shapes that you use it for, the area of this would be just equal to dy dz on this particular face, right? Etc. And so what you can do is you can end up writing a conservation equation, and I'll get to the punchline. The punchline is that the conservation equation that you get from using this on this particular geometry is something like this. The rate of change of density, so in other words, we typically assume that the volume doesn't change with time. And we have a term which is density times velocity in the x direction as a function of x plus density times the rate of change of velocity in the y direction with y plus density in the z direction with z equals to 0. So this is an expression that is conservation. So we're only talking about conservation of mass. And this is the statement of conservation of mass in a differential form. So in other words, instead of this being kind of an integral component, we've written it as a differential component. I suppose we should check whether my equations are right. We could do that, right? Just by dimensions. So what are the dimensions? So this is, density is kilograms per meter cubed, and time is seconds. So this is, these other terms are kilograms per meter cubed times velocity, which is meters per second, and this is meters. So we can't guarantee that this is right, but at least if the dimensions are right on both sides, these terms have a fighting chance of being correct. So I think it is correct. And I won't do it here, but if you throw, for instance, Darcy's law into here, and you might not know what Darcy's law is, but that doesn't matter for now. It's just a way of linking a change in pressure as you go across the system as a function of a permeability and a viscosity. If you throw this into these expressions, you end up being able to get a single equation which is written in terms of pressure, the fluid pressure that you have in a porous medium or that you'd have in the air around a plane for that matter. And this is really a statement of the amount of head losses you have in a system. You have to apply a certain pressure to be able to move fluid. So it's intrinsically, this is kind of equal to the head loss thing that we have. And so the bottom line is that you can use expressions that you get, which you will use. It'll be the diffusion equation, and you'll use it if you're doing 452, Geoscience 452, you'll talk about this in terms of hydraulic conductivities and specific storages. If you're a petroleum engineer, you'll talk about this in terms of fluid pressures and compressibilities of fluids. But this is the expression that you ultimately use to substitute Darcy's law into. And it's exactly the same as these expressions that we've used for rudimentary conservation of mass, a more sophisticated way of writing conservation of mass, and ultimately writing conservation of mass just for a little cube that happens to be dx, dy, dz in size and is exactly analogous to this expression. And so the bottom line of this, if I run these things again, is it allows you to be able to divide systems up into a whole bunch of small cubes, and you look at masses into the side of the cubes, masses out of the side of the cubes, and to be able to figure out exactly what's going on. I think it's more apparent maybe in this thing here, perhaps not in this one. I think it might be this one actually. If they do. So this is just a hose that's squirting around. It's kicking water out. We're keeping account of these particles. You could, if you wanted, think about this being a whole bunch of these little blue balls that I have being kicked out of something. They break into droplets depending on some particular laws that you apply. And they're really quite sophisticated codes around to be able to do these kinds of things. And I think this perhaps, hopefully this one says even more. And of course then you can render them so you actually look at things which you can use in movies, which of course is how they do these things in movies. So in movies when you look at water flowing, then it's not just arbitrarily, there are some rules that go to be able to define exactly what's going on. And there was one of these that had kind of a grid that it showed, and I'm not sure exactly whether it's this one or not. But they're basically doing the same thing. So you take the whole field of view that you're dealing with it, you divide it into a whole bunch of little cubes, like this, like you could imagine, well, no, not like this. And then you account for fluid flowing into and out of those cubes with some kind of law for head losses in the system, so that the system ultimately comes to rest. And so there are very sophisticated ways of doing this. Then you squirt some water all over it out of the hose, and you're able to follow that behavior. So, you know, stuff that we won't really talk about in this class, but the rudimentary components of it are quite straightforward. You divide this whole field of view that you can see here, say into a big cube, you subdivide it into subcubes, and you just account for the fluid transferring between each of those cubes, and then you paint it up in a nice way to be able to accommodate it. It's nothing more than that. So this is the deal. So where are we? We are 8, we're actually 8-3, but don't tell anybody. And so let's talk about porous media flows. And actually it occurred to me, let's look at this first. I had something here, let's see if we'll play. Where are we? So this is the idea. So this happens to be, so Ingrain is a company. We used to have, my colleague Brian Grader used to work here. He went to Ingrain to be their chief science officer, I think is what he is now. Certainly going to have a more plump retirement than I ever will, I think, in working in a company that probably generates a decent amount of cash. So the idea here, chips come up the wellbore. You CAT scan them when they come to the surface from the drilling, you know, tiny chips. You map out exactly where the pore spaces are, and then you use digital models to be able to recreate what the permeability might be in these very tight shales, for instance, if you're looking at shales. And so this is just an example of the kinds of models that you'd use to be able to do this. I think these kind of open areas here, these are the grains. These are the fluid parts of the stuff flowing between the grains. I think this is water with a gas phase or an oil phase in between them. And so when you see these things necking down and opening up, it just means that there's something coming in to fill the void, either as gas or as water. And so that's one way to look at these. But typically what we do is you use that to determine what the properties are of that little tiny chip. You assume that those properties pertain to a block that's maybe a meter by a meter, maybe a kilometer by a kilometer, doesn't matter. And then you use those properties to be able to say what you'd like to say about this, and that would typically be how much, whoops, you'd like to be able to say maybe, did I move to another one? I don't want to see that. Maybe very interesting to watch, but I don't want to see it. And then you use that to be able to say something about the system. And what you might want to be able to say is how much comes out of this face as a function of the pressure drop that I apply across it, and how do I use that in a bigger model to be able to say what happens to a remediation system or an oil field as I suck water out of the system and change the fluid pressures in the system. And so what we can do is we can use basically kinematics with a little bit of a twist to be able to solve a problem like this. And so what we can do is we could look at conservation of mass. And what do we know about conservation of mass? You'll recognize this expression, of course, right? Probably, do I even have to define the terms? We've used lowercase m recently, right? But you know exactly what I mean. This is our expression for conservation of mass. So what we could do is we could go back to that little system that we looked at, and we could define behavior in a slightly different way. We could use our control volume, instead of being this random control volume that we draw around a system, we could use our control volume to look like a cube, just like the cube we looked at on the in-grain stuff. We look at behavior in the x direction, the y direction, and the z direction. We could put a length on here, which is just defined as these individual lengths, right? So nothing terrible so far, right? We could look at the flow velocity that comes out of here, which would be Vx. The flow velocity that goes in here, which is Vx. But let's not limit ourselves to the fact that the same velocity has to come out that goes in. And so let's do what we've done before when we've talked about other things, have a change in this velocity, which is some small magnitude. And so this is the change in velocity as it goes across here, and we can see whether that can actually happen. And what else would we want to have in this system? Oh, that's fine. We could also do this, multiply it by 1, right? Done nothing more than multiply that by 1. And that defines our kind of control volume. So let's say that we're not going to allow the volume change to change of the control volume. So this is going to be 0. And so what we can do is we can look at each of these individual terms. So we want to have a term that represents the density change. And mass balance. And we know that m dot is going to be what? It's going to be equal to the velocity times density times the area, right? That's just our particular term for that. So if we wanted to write this out in some way, we could look at each of those terms in separation. And so what would this mass balance term look like? Well, how much do we have going into this upstream face? We have the velocity in the x direction, we have the area, and we have the density. And on the downstream area, we have the velocity in the x direction plus a change in velocity. Right? Times an area times density, and that equals what we're going to call mass flow rate. The velocity, it's into the system. The sign convention says if it's going into the system, the unit outward normal is negative, so this is negative. What's the cross-sectional area of flow? Well, it's going to be this area here, which is the same on both sides. So area is going to be equal to dy times dz. And what's this velocity here? Positive out of the system, so this part is positive. This is negative, they cancel out with each other. And therefore we're left with just one term. So the mass flow rate is just equal to positive change in velocity in the x direction with x times, this is the same area, right? This is dy dz, and so it's dx from here, dy dz times density. So we have one term. The other thing that we have is we need to deal with this term here. So we need an expression to be able to figure out exactly what density change is. So what's that going to be? So we have, well, let's write it out in longhand. Density change on a volume, just by writing it differently, is this, right? Change in density with time times the volume. We've just rewritten it out kind of in longhand. And so what do we know about this? Well, you remember we talked about density changes before in terms of compressibility. So if you remember back to the first week that we met, we defined a compressibility as being, we chose to define it not as a compressibility but as a bulk modulus. And that compressibility term was a change in density divided by an original density with a change in pressure. It's a P on the bottom, not a rho. And so we could rewrite this, for instance, so this is compressibility. This beta term is compressibility. So what we could do is we could rewrite this by multiplying both sides by rho 0, in which case we'd lose this. So this is density over pressure. And we could also multiply by 1, which is all I'm doing there. So now we have a term, which is this, which is exactly the term that we need here, right? And so if we rearrange that, what do we end up getting? Let's rearrange it in terms of this. We end up with the original density, the compressibility, multiplied by this term here, which is pressure over time. Pressure over time. And that's equal to just this value of rate of change of density, not pressure, with time. And so conceivably, we could substitute this in for this expression here. And so if we do that, and we write out this expression, and add it to this expression, right? Well, let me just write it down. So what is the term? So it's the volume multiplied by change in density over time plus mass and equals 0. And if we substitute these terms in here, we have density 0, compressibility, change in pressure with time. So this is this term here, plus the mass rate of change, which is just, I'm going to write it slightly differently, change in velocity in the x direction with x, which is this term here. What's this? Times volume times density equals 0. I've missed out a term, right, because it's actually the product of density and volume. So actually I need to put this term up front. And then if I get rid of this, if I make this a reference density, then I can kind of get rid of that as well if I wanted to. And all the final expression I have is some compressibility term, some change in pressure with time, plus change in velocity in the x direction with x. I'm going to write this over here as equal to 0. So we've done it in one dimension, but you could do the same thing in the other directions as well. And so what would happen if you did that, you'd end up with change in velocity in the y direction with y, and change in the velocity in the z direction with z. And so that's the fundamental expression that allows you basically to write the equations of mass balance. It's continuity. It basically says that volume in equals volume out, except for accumulation of mass. Mass in equals mass out relative to any accumulation of mass. And so that's the fundamental expression that is used in porous media flows. And the way it's used, I guess how are we doing for time? We're doing fine. Is by realizing that this is mass in minus mass out equals mass accumulation. That's all. It's written in terms of pressures here, so we'd like to be able to define this whole thing in terms of pressures. So how do we do that? And what we use is a law, and it's a law you might have heard of, Darcy's law. And so what it requires is that we do just this. So you take a piece of core, and you allow some fluid to flow through that core. And relative to some datum, you maybe keep it at the same elevation both upstream and downstream. You apply a pressure to it, which would be P1 over gamma. You apply typically a pressure differential, which is lower. And there's no pump in the system, but we could also, since it's not constricting, you could also have a V1 squared over 2G, and you could also have V1 squared over 2G. It has to be the same right here. V2 squared over 2G, right? So by the fact that it's not changing in area, as you go downstream, upstream to downstream, the velocities have to be the same for continuity. But what happens in this is that there's some head loss that occurs in the system. So this would be what we've called our hydraulic grade line. This would be what we've called our energy grade line, which remains constant. But what's this term in here? It's our head loss, right, in the system. And so usually we don't describe this behavior in terms of head loss. What instead we do is we look at the gradient of this change here that occurs over some length in the flow direction. And there's some change in pressure divided by unit weight in this particular case, but you could also convert that into a pressure change. And Darcy's law basically says that the velocity that this thing comes out of the bottom at, V2 in our particular case, is equal to two coefficients, a permeability and a dynamic viscosity, times the change in pressure with length. And so you can run this experiment and you can apply these conditions. You can apply an upstream pressure, a lower downstream pressure. You can measure the velocity that comes out. So you have this. You've applied a pressure, you know the length of the sample, and if you know the viscosity of the fluid, you can calculate what the permeability is. And the permeability, in this case, is defined in units of meters squared. And some people would know them as Darcy's. But the bottom line is, the important thing is that what we've done is we've defined a velocity in terms of a fluid pressure. And so what we can do is we can substitute this back into this expression, and the final expression is that we'd end up with a compressibility term, a rate of change of fluid pressure with time. It's a minus sign. Why is it a minus sign? Well, it's a minus sign because if you look at this being the x-axis, and if you look at this being the pressure axis, then this pressure change is a negative pressure change, but it gives a velocity v2 in the positive x direction. So it gives a positive velocity. Velocity is a vectoral quantity, and so the negative sign is just the fact that fluid flows from high potential to low potential. There's nothing more than that. And so if you do this, you'd end up with an expression that says d rate of change in x is equal to this, dp dx. And you can do it for the other directions as well. I won't, and you can add the one for, whoops, y. Oh, for completeness, let's just do it. dz, k over mu, dp. It's very quiet. You guys, hands are hurting from writing this down. So that's basically the expression that you'd use to be able to solve the flow equation. So we've done nothing except for conservation of mass, right? We haven't solved for momentum. We've kind of locked in the fact that we can account for frictional losses in some approximate way by using a coefficient which allows us to do that, which basically says that the frictional losses, instead of being proportional to the velocity squared, they're basically proportional to the velocity. You double the velocity, you double the frictional loss. And so that's what's perfectly adequate for porous media flows, because in these cases, basically the term v squared over 2g is much, much smaller than the other terms for pressure and for elevation. I suppose you could write these together. Or changes in the velocities. So the velocities will be very small, so changes in the velocities can only be small, and the magnitudes of pressures in the system are also similarly small. So what we've done is we start off with Reynolds transport theorem. It defines an absolutely arbitrary control volume size and shape. We've chosen to apply it to this cubic control volume, and we've ended up with an expression which defines our behavior in terms of a single differential equation in one variable, one dependent variable, which is pressure, which you can solve. And the solutions for that allow you to be able to solve for problems in petroleum fields or flow into wells for groundwater remediation. If there's no change with time in the system, then this differential expression, which is really the basis of what we use to talk about kinematics, is just a statement that volume in equals volume out. And so this you can think of, if you write it in two dimensions, right? A very easy explanation of this, dx plus change in velocity in the y direction is equal to 0. So the easiest way to think about this is to take this little cube that we have, just look at the side of it, where this would be, I guess it'd be plan view, right? Because it's x and y. And if you take this face here, and you move this with some velocity vx, and you hold it anchored here. Think of this either as a velocity, which it is, but you could also think of it just as a displacement. Much easier to think of it just as a displacement. So in other words, at this point you fix it, and then so if you plot velocity in the x direction with x, it has some amount here, and it's 0 here. So in other words, you're just taking a sheet and you're stretching it so that instead of looking like this square, now all of a sudden it looks like this, right? And so if you do the same in the other direction, in the y direction, this is Vy. So in other words, you take this portion here and you move it some amount so that now, when you've pulled it, it now looks like this, then that would look like this, right? This would be Vy, this would be dy, because that's what this length is, right? And this would be dx. And so the slope of this line, if you like, is dvx dx, right? So the simple explanation of this is if you have a piece of rubber and you stretch it, you know what's going to happen. It's going to shrink in the other direction. And so this statement is really just that. It's saying that if you stretch it in the positive direction to make it longer, the only way that this volume of this material can stay the same is if this shoots in by the same amount. And this shooting in by the same amount would be a velocity in the negative direction, and it has to equal the same amount as this. So this statement isn't anything more than that. And so what we'll talk about next time, I guess we didn't quite get to it, is how we can use this to be able to draw the kind of relationships, I guess it was on the other screen, the kind of relationships that allow us to get networks of streamlines that allow us to solve problems that are actually moderately useful. And so certainly if you're in petroleum engineering or if you're in environmental systems engineering, a very large part of your future careers will be evolved around this basic expression. And so to see where it physically came from, enjoy. That's it.